Hey everyone, welcome back to Tyler Maxwell's chemistry class. Today we're going to be learning about chapter 7, which is dealing with electromagnetic radiation, aka light. And light's cool because it exists as both a particle and a wave. And we're going to focus mostly about the wave portion of light. And waves have distinct properties. One of those properties is called wavelength. And that's just the distance between two peaks in a wave. The other property that we're going to be learning about is frequency. And frequency is the amount of peaks in a wave that pass through a point in a given period of time. And you can think about it as how many peaks are going to pass through my pen as the wave is traveling in a given period of time. So as your wavelength increases, the frequency decreases. And as wavelength decreases, well, frequency increases because there's more peaks that are going to pass. So frequency is given the term nu, and wavelength given the term lambda. And these two properties, we can relate them through the equation C is equal to nu times lambda, where C is the speed of light. Which is a constant at 2.99 times 10 to the 8 meters per second. So this is a constant, C, and that's the speed of light, 2.99 times 10 to the 8 meters per second. So the units there are very important because that means that our wavelength has to be in units of meters. Okay, that's really important. And our frequency has to be units of 1 over seconds. As you can see, meters times 1 over seconds is going to give us meters per second. So that's really important because a lot of times we're going to be given wavelength in another unit, usually nanometers, so we have to convert the nanometers to meters before plugging into this equation. So the other thing that we can calculate is energy. So light of different wavelengths has different energies, and this can be observed through UV light. Think of UV radiation as the kind that can burn your skin, but regular visible light is not harmful. That's because UV radiation has a lot more energy than visible light. So UV radiation is like that, and visible light is like that. So light with shorter wavelength has higher energy, and longer wavelength has lower energy. So we can calculate the energy of light of a certain wavelength through the equation E equals h nu, and we can also write E equals h c over lambda. And this is the same equation, we're just subbing in this into here, where E is your energy, and H is called Planck's constant. So H is equal to 6.626 times 10 to the negative 34 joules per second per photon. So that's just another constant. It's called Planck's constant, 6.626 times 10 to the negative 34. And energy is joules, just regular energy. Okay, so let's use these two equations to solve a quick problem. So say we have a laser, 685 nanometer wavelength. What's the frequency? And what's the energy of 1 photon and 1 mole of photons. So first thing, what is the frequency of the 685 nanometer wavelength? So we want to use our C is equal to wavelength times frequency, but remember C has units of meters per second. So we need to have our wavelength in units of meters. So we need to convert this nanometers to meters. So that's going to be 685 times 10 to the negative 9 meters times our frequency is equal to speed of light, 2.99 times 10 to the 8 meters per second. So we just got to divide both sides by our meters. And that gives us our frequency of 4.34 times 10 to the 14 s negative 1. So there's our frequency. Now, if we want to solve for our energy, we need to use this equation. Well, we can use either one of these, actually. We can use our wavelength or we can use our frequency. Here, since we've already got frequency, we can use our E is equal to H, which is 6.626 times 10 to the negative 34, Planck's constant, and then our frequency, 4.34 times 10 to the 14. So when we multiply those together, we get the energy of 1 photon, which is 2.9 times 10 to the negative 19 joules. So if we wanted the energy per mole of photons, we just multiply that guy by Avogadro's number. And then we get times 10 to the 5 joules per mole. So that's the amount of energy per mole of a photon of 685 nanometers wavelength. Alright guys, hope you guys enjoyed this video. Make sure you like, comment, subscribe, all that stuff. And until next time, I'll see you guys later.